Okay, so another review session for APC. In this case, we're going to look at rotational mechanics. Rotational mech. So this is one of those key things that right now at least is focused on APC, but not in APB. I think next year, as APB is being switched out, rotational mechanics will show back up, so this may get additional mileage down the road. In the end, rotational mechanics is tricky and difficult to deal with, but if you can keep the basics down, you're usually in pretty good shape. The biggest things, and we'll talk about that with the conceptual stuff, but the biggest things are, as long as you're familiar with how things work in straight lines, for the most part, you just need a small adjustment to make them work rotationally. Biggest thing that we need to start off with, and one of the first things that I'm going to point out on this, is the idea of what happens to your mass. Now, we talked about that in class. When it comes to rotation, it's not just how much mass you have that makes you resist changes in your rotational motion. It's how that mass is distributed. So the heavier you are, the more mass you have, and the wider it's spread out, the much harder it is for you to change your rotational state. In general, there were a whole slew of moments of inertia, I. On the exams and in general, you'll encounter people who call this rotational inertia, which is totally fine. Knock yourself out if you want to do that. But seriously, type in Google rotational inertia, and the first 2 or 3 links will say moment of inertia instead. That's the standard term for it. Moment of inertia, which describes something's resistance to a change in its rotating state, how it's spinning. Now, the main one that I'm going to provide us with here is for a point particle, and then also this works for a hoop. Okay? So, this will be equal to mr squared, where m is the mass of the object, and r squared is for the point particle how far it is from its center of rotation. So at my center of rotation, I've got an object going around this point here, something like this. My object's out here, and it's spinning around that. Then r is that distance from there. Okay? Most of the moment of inertia equations are going to be something like this. I'm going to put in an asterisk for it could be anything, old programming wildcard things. So moment of inertia usually looks like some constant, maybe c, times mr squared. For instance, a solid sphere, the solid sphere has mass kind of in the middle where we want it to be to keep a low moment of inertia, and then spread out. It's a pretty good distribution, so it's got 2/5 mr squared. It's a little bit less than half. The next one up was the disk, or the cylinder. That was at 1/2 mr squared. And we have the hollow sphere, which had pretty much all of its mass on the outside, which was 2/3 mr squared, I believe. So we had a list of different types of ones that were pretty common. Doesn't hurt to be familiar with them, because they can be really hard to derive again, especially for things like spheres. Pardon me. But the big ones that you really want to be familiar with are how to deal with the point particle, because that one comes up a lot. And knowing the general form is definitely going to be a good investment. Now, while that one's very important, I'd say the next is probably, it's arguable that it's equally important. You can't really do any mechanics in rotation if you don't know the equivalent of mass, how it's going to change, resist changes to its rotational motion. But the other big ones, and we talked about these specifically in class, delta x, our displacement equals theta r. Our velocity equals omega r, where theta is our angular displacement. When we're talking about spinning things, everything is angular. We keep track of, say, for instance, how far this guy has moved. If he starts here and ends up over here, then we have him sweep through this angle theta. That's his displacement. How quickly he does that, that's his angular velocity, or angular frequency, right? Angular velocity makes a little bit more sense in this format, though it turns out that omega from angular frequency, from simple harmonic oscillators, actually functions identical to this. And finally, our acceleration, these are all linear translational ones, equals alpha, our angular acceleration, times r, where r is the radius of our spin, basically. Spin or circle that we're moving in, because usually you're dealing with something rotating, going in a circle in one format or another. Okay? Although it isn't always like an object going through circular motion like we looked at before, because often you can have a hoop, like a wheel or something, and it's physically rotating. And we could look at one point on there to see how much all of it has angularly displaced. Now, big thing on this, we've talked about it, and it's fundamentally important when you're dealing with all of these angular values, theta must be in radians. And in our class, I made it a point to say, even though radians are not an actual unit, go ahead and treat them as though they are. So when you find the angular velocity, omega, it would be in units of radians per second. Now when you convert it over to other stuff, you're free to drop the radians out, but it's important to remember the radians per second, because the radians will also tell you when you're doing things like converting over to revolutions per minute. That tells you that, hey, one revolution, that's one complete circle. In radians, I need 2 pi. You'll need a factor of 2 pi to get that converted over. Now, in general, these are pretty good relationships. They'll hold in almost every case of rotational mechanics, and they're pretty safe to rely on, with the exception of rolling with slipping. Basically, as something is rolling but also sliding, you will not necessarily have these relationships. In fact, you won't have these relationships, because if you have these relationships, they go with rolling without slipping. Now, if you need to deal with a circumstance where you have rolling with slipping, you'll just set up relationships, and it'll continue rolling with slipping until it satisfies one of these equations. And so rolling with slipping will set up some of our differential equations. You'll find out what, pardon me, rolling with slipping means that the object will have a force of kinetic friction, as your rolling object will be slipping and sliding on the surface beneath it. You'll have kinetic friction, assuming that it's not a frictionless surface. If that's the case, then you'll have some equations that you could set up where you'll do your sum of forces, and that will most likely be your force of kinetic friction, and that'll be equal to ma, which is equal to m dv dt. There are those mechanics relationships that I mentioned. And we'll see that these guys, exactly like their counterparts, have the same type of relationships. We'll also have that there's a torque making it change how it's spinning, and that's our force of kinetic friction, and that will be applied at usually the bottom of the circle here, so it would be some distance away from our center of rotation of r, where r is the radius of the hoop or the ball or whatever you're dealing with. This is Newton's second law in rotational form, so our sum of torques equals I, our moment of inertia, alpha, where this is going to be equal to I d omega dt. And now you can go through and you can end up with relationships where it'll continue rolling with slipping, where friction is going to make it slow down, but start rolling faster and faster until finally it reaches one of these conditions, actually all of these conditions at the same time. These correspond to rolling without slipping. Pardon me. All right, so that's a review on that, and also something where you want to keep track of omega equals d theta dt, and alpha equals d omega dt. We'll also have the similar calculus relationships. But again, this reinforces the idea that if you're familiar with how it works in straight lines, it's an incredibly simple replacement for rotational. The harder parts of rotational are getting the conceptual stuff down. Okay, so we've already shown it here, but the next equation that I would recommend is Newton's second law for rotation. Sum of torques are going to be equal to I alpha, which is also going to be equal to dl dt, where L is our angular momentum. We spent a good amount of time talking about that. Now, one of the very useful equations that has kind of limited use, this is the angular momentum of an object moving in a straight line, so it's just moving in a straight line, but it's the angular momentum about a point. So basically we've got some point here, and we have an object moving in a straight line related to it. Now this equation looks like this. We've used it many times. It's a simplification of the broader form, which is L equals R cross P, where I've got mvr, where this is my mass, times my linear velocity, so that's my linear momentum, times this r is going to be specifically the perpendicular distance that your path of the object takes from your center of rotation. Now this is a very specific equation. You can use this for particles that are moving in a straight line about a given point. The broader and more universal equations, but not necessarily easier to apply, are going to be this. Angular momentum is r cross p, where this would simplify down to rp sine theta. And you can see we're actually ending up with the same exact thing up here, where we have r, p is that guy, and sine theta, but we're using the r that is going to be at a right angle to it, so sine of 90 is just going to be 1. And so this is a simplified form of this. The main reason that I bring this up, because I don't usually try and give you the simplified forms, is because this one is eminently more useful, and if you're comfortable with it, it will save you time having to simplify all of this guy down. Because you may start off with your object back over here, and so you're going to be looking at some r back over like this. You'll find the angle theta between them, and it'll be a bit of a mess. It turns out that when you evaluate all of that, it's going to give you the exact same value as this guy. All right. Finally, one of the other ones. Torque equals r cross f, which equals rf sine theta. And we saw that a little bit earlier when I had the equation that I brought up with friction, for instance, where I had the force times its lever arm, how far away from the center of rotation it's being applied. And we also have to pay attention to the angles that they're going at for friction. Back when we had this guy, I would have friction pointed off maybe this way to the left. And my lever arm would come down like that, so I'd have 90 degrees between them. Sine of 90 is 1. Basically, we get a maximum at that point. All right. So, biggest things to keep in mind. Difference between mass and moment of inertia. Now you can't just think of how heavy something is. Mass is not the name of the game. You've got to pay attention to how that mass is distributed, which is your moment of inertia. So now you can have something fundamentally change how it reacts to motion rotationally simply by moving some of the mass around. One of the examples is when you have a figure skater spinning, they'll draw their arms in and start spinning faster and faster. If you remember, we actually did that in class with one of the chairs and some dumbbells. Okay, that's a huge one. Your replacements and how to be able to use those, where, green. Your displacement now becomes simply theta. You could even have a delta theta, the change in angle that you sweep out. Your velocity now becomes omega. Okay? For the most part, they're just point-by-point replacements in your equations. The biggest thing to keep track of is this change in mass, because it's no longer mass, it's the moment of inertia. So it's really going to change. It becomes harder to think of for a set mass which one's going to elicit what changes in your motion. Okay? One of the other things, one of the big ones, is dealing with angular momentum. The concept that you can have angular momentum while moving in a straight line. And we talked at length about that, so make certain that you review, question, come and ask me if you're having trouble with that. But that's one of those key things that really derails people's ability to solve problems. Angular momentum, even when something's moving in a straight line, if you're looking at it from a given point, it still has, I should say, angular momentum. And when it comes to angular momentum, just like with regular momentum, translational momentum is conserved so long as there are no significant external forces. Our equivalent in rotation is angular momentum is conserved when there are no significant no significant external torques. Big thing to remember on this is you can have all kinds of forces, but if they're always directed through your center of rotation, they cannot be torques, and therefore they will not actually change your angular momentum. This leads to the ideas of Kepler's laws, among other things. So when we look at the sun, for instance, and a comet going around the sun, we have it kind of on a long elliptical orbit like that. Its angular momentum is conserved because the only forces acting on it are gravity. It has a force of gravity from the sun, and technically it applies a gravitational force on the sun as well, but the center of rotation for this guy is actually always going to be in between the sun and the comet. Technically you end up with a barycenter, probably with this system actually inside the sun. But both of them will continually have this force of gravity. We call it a central force. In other words, they're always pointed from one of the bodies to another. It will always be pointed through the center of rotation for both objects, which means while it is a very significant external force, and your translational, your linear momentum is not conserved. Actually, yeah, we'd have to play around with that some depending on the definition of our system. But most importantly, since these are, they're very big forces that make this guy speed up and slow down, but because they're directed through our center of rotation at all points, our angular momentum cannot change. You can have very big forces applied onto materials, but they will not end up necessarily changing their angular momentum. It depends on which way those forces are pointed. These added levels of complexity make rotational mechanics a bit harder to deal with, but take a close look at the sample problems that we've done, the previous exams that we've had, and ask me if you have any additional questions.